Let's do a fluid mechanics problem today. This one is out of the Munson textbook, so it's 2.8.10. And what it is we've got a wall that's being held upright by this weight right here, and it's got water that's pushing against it. And notice this is pinned here. All right, so that detail is important. So what we want to do is find the weight W right here that's needed to hold this wall upright. And we're told the wall is 10 meters wide. So that means it like goes back into the page 10 meters. Okay, so this is just like that front view. All right, so first let's draw a free body diagram. All right, since we're gonna have forces on here. So let's see what we should have in this diagram. So let's draw it of just the wall. All right, so there's the wall. And now let's label our forces. Okay, so first of all, it's pinned here. So if we've got a pin at that point, what forces should we have? Should have an X component and then an A and then a Y component, right? So let's have a Y and then a X. I just chose those directions. I have no idea if those are the right ones or not. I just usually pick the positive directions. All right, what else do we have? Well, what about up here? So this is one cable, right? So it's gonna have a force in there. So basically this is the tension in the cable. So if I were to look at the weight, right, so that's the weight right there, and look at it, I've got W and then I've got tension, right? Well, you can only have one tension in a cable. So if that's the tension here, that's got to be the tension in this part of the cable also. So if we do equilibrium, T minus W equals 0, so T equals weight. So I can come over here, put weight right there. All right, so now we've got that. And then what else should we have? Well, we've got that water, right, that's pushing up against the wall. So that is going to provide some sort of force, right? So let's go ahead and put that on here. We'll find its location in just a minute. So let's just put it here. Let's call it F. Okay. So now what we need to do is we need to calculate what F is, and then I need to find its location. All right. So let's go ahead and do that. We don't really need to worry about what AX and AY are, because when we do our equilibrium equation, we can, take a moment about this point and not have to worry about those two. So only thing we really need to worry about right now is getting F. Now that is a horizontal load, right? So the equation for that would be gamma HC times A. All right, so remember gamma, you could also find that with rho times G. So rho would be density, G is just acceleration due to gravity. Now this is water. All right, so gamma for water is going to be 9.81. That's kilonewtons per cubic meter. All right, so we've got that. And let's rewrite this 3. It's hard to read that. And then we need HC. Well, what do we think HC is? Well, let's come over here and look. Actually, let's do it up here. Okay, so HC, what that's going to be is that's going to be the distance from the top of the water to the centroid of the area in contact with the fluid. Okay, so this right here, we're in contact with the fluid, right? So that's the region that's touching the water. And the centroid of that region right here is going to be right in the middle, right? So HC is going to be the distance from the top of the water down to that centroid location. All right, so that is HC. Okay, so what value would that be? That would be 2, right? Okay, so this is going to equal 2 because, that's half of 4. And it's hard to read that there. 2 meters. Okay, so HC is going to be 2. So let's plug that in, 2 meters. And then now I need the area. Now this is the area that's in contact with the water. Let's make a note. All right, so that's in contact with the water. All right, well, I know the height is 4, right? And then I need to know how far back it goes into the page. Well, that's 10. Because if I were to look at it kind of like this is 4, that's 10. So all of this is in contact with the water. So this is the area I want. All right, and then how do we calculate the area of that? It's just a rectangle, right? So we're going to have 4 meters times 10 meters. Okay, so let's go ahead and multiply. We get 784.8. That's going to be kilonewtons, because notice all your meters here cancel out. So this is our force, but I don't know where that's acting on the door, or not the door, but this wall, right? So I need to know where it's acting. All right, so first thing I want to do, let's label the centroid that we have right here. So I want to put this on this diagram. So let's just say it's right here. Okay, and let's kind of draw the water line. There's the water line. So let's say this is 2 meters. And I need to know what this distance is, right? Because this force is going to be below the centroid, because the more depth you have, the greater the force is, right? So it's got to be below the centroid. So I need to know what that distance is. So this distance, let's call it YCP, okay? And YCP has an equation we can use to calculate that. So it's going to be negative IXX, so that's just moment of inertia about the x-axis, times sine of theta, we'll talk about theta in just a second, over HC times A. All right, so the negative tells us we're going below the centroid. So let's put a note. So below centroid. And then IXX is just your standard moment of inertia for your area that's in contact with the fluid. So here I've got a rectangle. Okay, so for us we're going to have negative 1/12 times the base, which is the 10, and then the height, which is 4, will be cubed. All right, so this is going to give me meters to the 4th here, because this is meters, cubic meters, right? So meters to the 4th. And then this angle theta, this is basically going to be your angle from the horizontal to your surface that you're looking at. All right, so for us, that would be theta. Okay, so theta is going to be 90 degrees, right? Because those are perpendicular. So we're going to have sine of 90. And what's that equal? 1. Okay. And then we're going to put it over HC times A. Now we already found both of those. HC was 2. And then area is the 4 times 10. All right, so now we've got that. Notice our units. We're going to have cubic meters in the denominator. We got meters to the 4th up here. So the unit that's left over will be meters. Okay, calculate all of this. And we get negative 0.667. And that's meters. So the negative, again, like I said, it just means you go below the centroid location. So we're going to go 0.667 meters below that centroid. And that's where this force is going to act. All right. So that's pretty much all we need. The last thing we might want to do is label the distance to the weight. Right, so it's 4 plus 3, so that's 7 right there. Okay, but now we're ready to solve. Okay, so I want to find weight. That's what we're looking for. Okay, I know what force is, the F, right? It's 784.8. So let's go ahead and get an equation. So I don't want anything moving, right? I want this to be in equilibrium. So I can use my equilibrium equations. And the easiest one to use is going to be to take a moment right here at point A. So let's call that point A. Okay, and if I do that, remember AX and AY, they go right through that point, so I don't really need to know what those are because they don't create a moment. Okay, so let's go ahead, let's look at the force. All right, counterclockwise is positive, so this one would be a negative moment, right? Because if I put that here and I hold on at A, and then I push to the right, it's clockwise. So that's going to be negative F. And then the distance is going to be what? What do we think that would be? Well, let's look. So I know this total distance here is 4, right? So from here to here is 4. And then I know this distance from here down, that's got to be 2 plus the 0.667, right? So this distance here has to be the 4 minus the 2.667. That's meters. Okay, so that'll be our moment arm here. All right, so that'll be our perpendicular distance because we need to go from here to A. All right, negative because it's clockwise. And then let's go to W. So W is what we're looking for, right? So that one's going to the left. So again, if I push that way, it's counterclockwise, so that's positive. And then what would that distance be? Well, that's going to be this 7 meters, right? Because that's the distance between where the weight is applied, this tension in the cable, and A, right? So that distance there is 7. And that's it. Set it to 0. Now, I know what F is, so we can plug in that value, right? 784.8, that's kilonewtons. And that's meters there. So one unknown, one equation. So now you can solve for weight, and you get 149.45 kilonewtons. So that's the weight we have to have in order to keep that door, or that, I keep calling it a door, to keep the wall upright. Okay, but that's how you go about finding it. So horizontal force, we'll use this equation here. Remember, HC is measured from the top of the water line, and it's always vertical. So let's write that down. And it goes to the centroid of the area in contact with the water, and it is always vertical. Okay, so that's how we get HC. Area is just the area of the region that's in contact with the water. And then this equation right here will tell you how far below the centroid that force F is going to be applied. All right, so hopefully that helps you kind of see what HC is and what the YCP is. Okay, because those two things are important to know. All right, so that's a short little problem. So I hope you liked it. I will see you guys next time.